8086 and 8088 interrupt. 8086 and 8088 processors, they are compatible with each other and they have a simple and versatile interrupt system. Every interrupt is assigned a type code that identifies it to the CPU. The 8086 and 8088 can handle up to 256 different interrupt types. In today's video, we discuss the 8086 and 8088 interrupt. Let us start. Welcome to our channel Engineering and Technology for You. If you are not subscribed to our channel, kindly subscribe and press the bell icon so that you get notifications for our future video. The topic for today is 8086 and 8088 interrupt. Let us start with the introduction. As you all know, interrupt is a method or mechanism by which the CPU provides service to the peripheral device which requests for the service. See, whenever the peripheral device needs service from the CPU, it will request the CPU. Now this request will come on the interrupt lines, and the CPU or microprocessor will respond to the interrupt with an interrupt service routine or procedure, interrupt procedure. So that is nothing but a short program or a subroutine that instructs the microprocessor on how to handle the interrupt. So when the device requests the interrupt, the microprocessor will handle the interrupt with the ISR and it will service the devices. Now 8086 and 8088 processor, they have a simple and versatile interrupt system. Every interrupt is assigned a type code that identifies it, and it can handle up to 256 different interrupt types. So the type codes will be from 00 to FF in hexadecimal and 00 to 255 in decimal. So what are the different sources of interrupts? So first, the interrupts can be initiated by devices external to the CPU. So there are two pins, NMI and INTR. So these interrupts, they are called as the hardware interrupts or external interrupts, because these interrupts, they are coming on the pins of the microprocessor. Then second source of interrupt is execution of interrupt instruction. So INT is the instruction, INTN, where N is the type number. So this type number will be given in hexadecimal from 00 to FF. So all the interrupts which are initiated by INTN, they are called as the software interrupt, because the interrupts are initiated by instruction. Then the third source of interrupt is from certain condition produced in the processor by execution of instruction. For example, here the division by 0, that becomes an exception. So such interrupts, they are known as exception or internal interrupt. We'll see the details of these internal interrupts when we actually go further. Let us see the sources of interrupts with the help of diagram. So first is the hardware interrupts. So we have two hardware interrupts, NMI, there is non-maskable interrupt. So that is external interrupt. As you can see, this is the 8086 8088 CPU. You can see the interrupt logic and other interrupts here, And this NMI, non-maskable interrupt request, it is external to the 8086 or 8088 processor. So it is called as the external, or it is a hardware interrupt because it comes from the pin of 8086. Then the second interrupt is INTR. So again it is coming from outside the 8086 and it is connected to 8259. So 8259 is nothing but programmable interrupt controller. And here the maskable interrupt requests are connected to 8259 by various devices. And whenever the device requests 8259, then 8259 will send the INTR signal, the interrupt request on this INTR pin of 8086. So that will be received by the interrupt logic, and then 8086 will respond to that. So these are the hardware interrupts, or they are also the external interrupts. Then you can see here we have the INTN instruction. So they will form the software interrupts. And these three, they are the internal interrupts. So here we have the single step when the TF flag is equal to 1. So this is used for single stepping or debugging the program in the form of single stepping. Then we have the divide error. So whenever the division by 0 is attempted, at that time this interrupt will be generated. So this is again internal interrupt. And then this is INTO instruction, or is the overflow flag interrupt. So whenever there is an overflow, at that time this interrupt will be generated. So these three are the internal interrupts in 8086. Then we have the software interrupt in the form of INTN instructions, and then we have the hardware interrupts in the form of NMI and INTR. So if you understand this, then it will be easy to understand the details of these interrupts. Let us go further. Dual facility of initiating interrupt. Now this is again another facility provided in the 8086 and 8088 processor. It is dual facility of initiating these 256 interrupts. So interrupts can be initiated either by executing INTN instruction. So again we have already seen that N is the type number, or the interrupt can be initiated by sending an appropriate signal to the INTR input of the processor. That means there is a dual facility. Either you can initiate the interrupt by executing a INTN instruction. So INTN, and the value of N is from 0 to 255 in decimal, or 0 to 00 to FF in hexadecimal. So total 256 interrupts can be initiated by the INTN instruction. And similarly, we can initiate 256 interrupts on the line INTR. So here, for interrupts initiated by software, that is INTN, type number is specified by the instruction itself, because in the instruction we will give the type number. Say for example, INT02, that is for type 2 instruction. And when we are initiating the interrupt through INTR pin, at that time will run the interrupt acknowledge cycle to get the type number. So this interrupt acknowledge cycle, when we run, the interrupting device should supply the type number through the data lines D0 to D7 lines when the processor requests the same through the interrupt acknowledge cycle. That means during the interrupt acknowledge cycle, we'll get the interrupt type number on the data lines. So here what is important is the dual facility, because this thing will confuse you later on. So totally 8086 and 8088 has 256 interrupts. Now this 256 interrupts can be initiated, one by INTN instruction and secondly by the INTR. So either of this we can use for initiating the, that's why we say that there is a dual facility of initiating the interrupt. So this should not confuse you. Then let us go to the interrupt vector table. So interrupt vector or interrupt pointer table, actually it is the link between a interrupt type and the procedure that has been designed to service the interrupt associated with that. That means here for 256 interrupts, we'll have 256 entries in the table, one for each interrupt. And the interrupt pointer table occupies first 1K bytes of low memory. Here what is the meaning of 1K bytes of low memory? It is nothing but starting from, say, the lowest address, that is 0000. So it will start from that address and the first 1K bytes, because 256 multiplied by 4, that is 1K. So each entry is having 4 bytes. That's why we are multiplying it by 4. So the total memory occupied will be 1K. CPU can calculate the location for a given interrupt type by simply multiplying type multiplied by 4. So for example, if you take, say, type 1 will be, say, 1 multiplied by 4, that is 0000. So in this way we can calculate the address for, say, any type of interrupt. Just multiply type by, so that will give us the address in hexadecimal. So that will be the address for the, say, interrupt location. Let us see the interrupt pointer table, then it will be clear to you. See here, so the first address we are mentioning is at 000H. So this will occupy from 000 to 003. So 4 bytes. And now this is the for type 0. Then for type 1 it will start at 004 and it will end at 007. Then type 2 it will start at 008, end at, say, 00, that is 11 in hexadecimal. So in this way the type 3, type 4, type 5, they will be occupying the address in the vector table or interrupt pointer table. So we have a dedicated interrupt pointers, there are 5, and then we have reserved interrupt pointers, there are 27 in number. So first 32 they are not used by the user. The remaining 224, they are available interrupts pointer for the user. And the last address will be 3FF. That is, total memory will be 1K. Now here we have shown this width as 16 bit. When we actually calculate, so each entry in the table is double word, that is 32 bit. So this is 16 bit, this is 16 bit. So it will have, say, the address, higher order address will be the base address of the segment containing the ISR or interrupt service procedure, and the lower order address will be the beginning of the offset. So this is the code segment base address, and this will be the IP offset, instruction pointer offset. So this is how the 4 bytes they will be used for one interrupt type. So type 0 will have the 4 bytes. Similarly, type 1 will have the 4 bytes. And as we have said, 32 vectors are spared for the various microprocessor operations, and 224 they are user defined. So here type 0 is nothing but divide error, and type 1 is single step, type 2 is non-maskable, type 3 is say it is for 1 byte INT instruction, type 4 is pointer overflow, say overflow flag for the, and type 5 is reserved. So we'll be discussing these dedicated interrupts in details, and then we'll discuss the other things with respect to interrupts, that is the priority of the interrupts. So let us first go to the dedicated interrupt pointers. Now as you can see here, the dedicated interrupt pointer we have, first is interrupt type 0, so INT 00. So the instruction for type 0 will be INT 00, and it gives us the divide by 0 error interrupt. So whenever there is a division by 0, or if the result of div or idiv operation is too large to fit into the destination register, at that time this error will be generated, and this will initiate the interrupt INT 00. Then type 1, that is for the single step operation. So if the trap flag, TF flag, that is trap flag in 8086 is set, the CPU automatically generates type 1 interrupt following every instruction. This is called as single step execution and is powerful debugging tool. So it will be used for the single step execution. Then the next is type 2, that is non-maskable interrupt. So here, when NMI pin receives a low to high transition, that is, it is edge triggered, that's why low to high transition, this interrupt will be initiated, and this interrupt cannot be masked or disabled. That's why it is called as the non-masked. Then we have breakpoint interrupt, that is INT 03 or type 3. So in this case, the breakpoint will be generated, and the breakpoint is used for debugging. So the execution will be up to the breakpoint. That means the program will be divided with the help of these breakpoints, and the execution will be carried up to the breakpoint. So this will help in debugging the large programs. Then we have the type 4, that is overflow interrupt. So whenever the overflow flag OF is set, if the signed arithmetic operation generates a result whose size is larger than the size of the destination register or memory. So at that time the overflow flag is set. We already discussed the flags in the previous video. So this type 4 or overflow interrupt is for indicating the overflow error. Again, there is INTO instruction is also used for this type 4 or overflow interrupt. So it is equivalent to type 4 or INT 0. Then let us go further. External interrupts. Now already we have discussed there are two external interrupts, INTR and NMI. There is non-maskable interrupt. Now let us discuss first the INTR in details. As we have already said, it is usually driven by the 8259 programmable interrupt controller. So there is a separate video on 8259 on my channel. You can watch it if you want to understand the programmable controller. So here you can see the 8086 8088 processor is shown connected to 8259 interrupt controller. So these are the data lines. Here it is shown as 80 to 87, and then we have the ALE signal, address latch enable signal, and then we have shown the INT pin of 8059 is connected to INTR pin of 8086 or 8088, and this is the interrupt activity. So whenever there is a request, now the request first will come from these inputs IR0 to IR7. 8259, it has the 8 interrupt inputs lines IR0 to IR7, and these are connected to peripheral device. So whenever the peripheral device needs some service from the CPU, it will send a request on this line. So when the 8259 gets a request on these lines, it will send the request to 8086 on the INTR with the help of this INTP. Then the 8086 will send the acknowledgement on this line INTA bar. This is a active low signal. Now when the acknowledgement is sent, at that time it will also give the interrupt type number on the data bus that will come on the. So then that interrupt will be lost. Let us continue with the INTR pin interrupts. So now here INTR interrupt is maskable interrupt. So it can be masked or disabled. So when it is masked or disabled, at that time it cannot cause interrupt. Now how it is masked? Say when the interrupt flag is cleared. Cleared means it is made 0. At that time, the INTR pin becomes disabled. Now, how to clear the IF flag or interrupt flag? It is cleared by the instruction, the clear interrupt instruction, CLI. So if you give the CLI instruction, it will clear the interrupt flag and it will disable the INTR pin. So once it is disabled, it cannot cause the interrupt. So that is what should be clear to you. Then how to enable the interrupt? So when interrupt flag is set, INTR will be enabled. And how to set the interrupt flag? That is with the help of set interrupt instruction, STI. So if you give the instruction STI, it will set the interrupt flag and the INTR pin will be, then it can cause the. So then let us go further. So when 8259 receives an interrupt on any one of the IR inputs, as we have discussed in the previous figure, it provides an interrupt request to the INTR pin of 8086. Then when INTR pin is enabled with STI instruction, the 8086 sends an interrupt acknowledge signal, and this will be sent on the INTA bar line, as we have already discussed. So this is the figure is showing the interrupt acknowledgement signal. So here we have the clock. So these are the different states, T1, T2, T3, then T1, T2, T3, T4. And this is the ALE line, address latch enable. It is going high during the T1 each cycle. Then this log bar, this is going low. And INTA bar, when it is an active low signal. So when it goes low, it will say whatever is on the data lines. Here we have the INT type. So this INT type, it will be sent on the data bus with the help of INTA bar going low. So this interrupt type, that will be simply a number in hexadecimal, is 00 to FF. So for example, we want say INT 12, then we'll have the number here as 12. Up to 32 we cannot use, so we'll have to make use of, if it is user defined interrupt, then we'll have to go beyond 32. So the number will be going with the help of this on the data bus. We have already seen the vector table. There we have discussed about these INT types. Then the next interrupt is the non-maskable interrupt, or NMI. So this is the input pin on the processor, and it has higher priority than the INTR. It is having the highest priority among the external interrupts. We have two external interrupts, NMI and INTR. So whenever there is a positive transition, low to high, then it will be activated. So this is equivalent to INT02. It is type 2 interrupt. So INT02H instruction and positive transition, low to high transition on NMI pin, it is same. We are activating the interrupt that is non-maskable. So this signal is generally used by the CPU for emergency events such as loss of power or memory error detection or bus parity error. So in these cases, the non-maskable interrupt will be initiated by the processor or 8086, and we cannot disable this interrupt. That's why it is called as the non-maskable interrupt, and it is latched by the CPU, and it is having higher priority than the INTR. We'll discuss the different priorities of the interrupt later on. The interrupt priority. Now, the internal interrupts. There are three interrupts we have seen. So, except single step, the other two, they are having higher priority than any external interrupt. And interrupt requests arriving on NMI or INTR, if it is received during the internal interrupt, that is divided by error, then this divided by error, because it is having higher priority. If you look at the table, the divide by error, the divide error, then INTN and INT0, INTO, that is overflow interrupt, they are having the highest priority. Then we have next priority for the NMI, and then for the INTR. The lowest priority is for the single step interrupt. So these are the interrupt priorities in 8086. With this, we come to the end of this video. If you have any queries, you can contact me on Facebook, Twitter, Gmail, Instagram, or on the website. Then if you like the video, press the like button, share with your friends, and subscribe to our channel Engineering and Technology 4. And don't forget to press the bell icon to get more videos, notifications about more videos on this topic. Then thanks for watching. Have a nice day.